So I'm delighted to have Nicholas Lane with us today, who's giving today's talk in the ELLIS series on machine learning. Nicholas is a professor in the computer science department in Cambridge, where he leads the machine learning systems lab, and he's also labs director of the Samsung AI Center in Cambridge. And today he's going to talk to us about machine learning in the data center and some of his views on how things might be different in the future, I guess. So I'll hand over to you, Nicholas.
Hey, thank you very much for the introduction, and it's a pleasure to be here. I'll just start sharing my slides. I think everyone can see it fine.
Yeah, we can see that.
Perfect. So let me begin. So today I'm going to talk to you quite a bit about work we've been doing to build up the capacity to do distributed machine learning. And in particular, I'll be focused on federated learning. And one of the interesting dimensions to this is that although the motivations for doing this often are related to, say, privacy and giving the user the capacity to control their sharing of their data, I think there's a much wider story to this, and that motivates us towards moving from the data center, where the bulk of machine learning is done today, to other more distributed paradigms, of which the one that I think is the most ready to sort of really roll out is federated learning. In particular, along this line, I'll be referencing a lot a framework we developed called Flower that really seeks to make it simple to innovate in this sort of direction and removes many of the obstacles that currently exist. And then at the end of the talk, I want to give you a few of the case studies that we've developed using Flower to do interesting work in the direction of federated methods. But let me unpack first this title. So when I talk about the machine learning data center, I'm referring to this current set of affairs that we all live in, whereby the vast majority of machine learning that we interact with on a daily basis, or even the ones that we kind of conceive on in research, have an underlying assumption that looks like this, where we assume that there's going to be a massive amount of compute thrown at some sort of neural network. There's this idea that this neural network is going to be trained via a lot of, a large collection of carefully curated labeled data. And the stand-in there is often ImageNet, but there are obviously other ones based on the task you're trying to aim for. And these models, by the virtue of the fact that they live in the data center, are very large, right? So there's these huge parameterized models that we use large GPU resources to train. And then this is the existing situation that you can't really escape from. So on the left-hand side of the slide, you'll see all these sort of everyday occurrences where people will interact with machine learning, be it doing a Google search for a particular image, be it every time they pick up their phone, where there are hundreds of models being used to drive the services of that phone, Alexa, even Netflix. You can't escape this situation of machine learning. And then what I want to posit to you, give you some food for thought, is that this paradigm has a huge amount of negative externalities that we're only really starting to really have an understanding of. And I think in, say, 10 years' time, when we look backwards to where we are today, where we relied so heavily on this type of configuration for building out and deploying and training machine learning, we're going to draw comparisons, I think, between this situation and other things that were popular in society that we pivoted away from. And so examples of this would be smoking. There was a time when it was fine in society to smoke. It was even encouraged by doctors. And there was adverts like this. And it wasn't until much later that we realized that there are a lot of different negative externalities that meant that we should never have been conducting in these that activity in the first place. I can pivot to another one. I could think of something like lead paint. It was used to be common to use lead paint in all sorts of type of decorations inside houses that could have negative effects on those who lived inside them. But as soon as we realized the negative effects, and as soon as we had replacements, alternatives to pick, we moved away from those types of technology, if you will, and never used them again. And then, of course, there's those that we do currently related to how we negatively impact the environment, the way that we try to fight against climate change, that we haven't unfortunately been able to move away from yet. But my point here is that The use of data centers, I think, will go down in history related into this basket of things that we wish we never did, but we had to for a period of time because we had no real alternatives. And so if I'm suggesting that the use of machine learning and in the data center has all these different negative aspects to it, let's start to look at what these negative aspects are. So of course, the one that's often put forward is that of user privacy. There are strong controls now on how data can be shared, and but the data center itself requires data to be collected centrally before the training can occur. And so that by itself means that users have to lose control of the data to somewhat before those models can be trained. And that's often the touch point, the touchstone that people will rely on a lot when they try to push for decentralized forms of machine learning. But this list that you see on the slide contains many other aspects I think we also need to pay attention to. So one of these is related to systems that use machine learning based models that live in data centers. So whether it's a device that you see this medical device used to listen to the breathing sounds or the heartbeats of patients, where the models themselves might exist and be deployed from a data center. It could be a robot that you deploy in the home or in the wild, where a lot of the intelligence might exist in the data center. The limitation here is that as soon as the connectivity is gone, well, then the intelligence of this device goes with it. And so these systems inherently are going to be brittle. They're going to be very potentially even dangerous if they can no longer reach the data center because their operation, the way that they function is no longer possible to occur. That's another reason why we need to move away from data center-based machine learning. There are others. I think something that goes hand in hand with the use of large-scale training and the data center is the reliance on carefully curated and importantly static data sets. And this has a lot of downstream effects, I think, on the models that are created. And so there's been a lot of discussion in the community about biased models. And this is going to be a naturally occurring effect if you have static, carefully curated data that needs to sit in a data center and train the model versus data that might be available in the wild, because there's always going to be a wide gulf between even the largest possible data sets we can collect and the data that is naturally occurring and constantly changing in the real world. Those two sources of data are always going to have a giant gulf between them that you can never completely cross over. And so therefore you'll need to think of ways that you can build models that are based on data from the edge that is constantly updating if we want to ultimately start to remove some of these biases that we see occurring. And finally, one that's more often talked about is the issue of carbon and energy efficiency. This is a study that many of you would have seen. This figure here from the bottom right is from a paper that came out a few years ago that was specifically talking about NLP models. And it was saying at that time, state-of-the-art NLP models, when you take into consideration some of the neural architecture search that's done on top of them, and when you train, singular model, you can end up with a carbon footprint that's equivalent to 5 cars driving around the US for their entire lifetime. And we know US folks love their cars and like to drive a long distance. So that's saying something. If the training of one single model that produces a SOTA NLP model to be used has the carbon footprint of 5 of these cars. And again, this is an extension from this paradigm of living in the data center, assuming large models and assuming to use a lot of GPUs. If we can find alternatives, well, then we're going to have the ability to start to sort of overcome this other negative externality. And so I think in sum, you could characterize this existing situation as a bit of a societal cancer that we should start to carefully consider alternatives towards how we can offer the same types of services, build the same type of computational systems, but in a way that does not have all these negative attributes. And so along this path towards thinking of an alternative, there's a few options available to us. So something that my group's been heavily involved in, I guess since about 2014 or 15, has been the development of what's called on-device machine learning. And so this is a setting where you train the models conventionally in the way I've been describing, but you then deploy them locally on the device. And so at inference time, inference happens through trained models that might exist on a phone, on a robot, in situ on devices. And so this goes part of the way to solving some of the problems I've talked about, at least the inference costs of energy, the inference costs of timeliness in terms of brittle systems I talked about earlier that are dependent on connectivity, they somewhat disappear. But of course, a lot of the negative elements still remain. We're still training these models on a static data set that's unchanging, that's inherently going to be biased, and so forth. There are other alternatives in learning that are being explored, but many of these are not really ready to be used today because there's an accuracy gap between the models that they can provide and what these existing forms of learning that are based in data center can provide. And so given this accuracy gap that exists between these emerging alternatives in learning that may not have these issues, they are also not ready for prime time. But where we have decided to invest a lot of our energy today is in a particular form of learning, many of which many of you would already have heard of, called federated learning. And so there's a particular form of decentralized learning by which we think we could start to replace, particularly with the right investment in solving the right research problems, we think we could start to replace many of the existing use cases that happen to reside in the data center, and by that means starting to address these negative externalities I mentioned before. For those of you who've never heard about federated learning, let me just give you in a few minutes just a quick summary of what are the key ideas. And actually, in one sentence, the key idea is that instead of data having to be collated in one central place and trained over with some training algorithm to set the model, alternatively, federated learning seeks to have data reside at the point of collection. So you could have institutions like hospitals, you could have banking authorities, you could have lawyers, you have any institution collect their own data, not share it, and then an algorithm that sits within the domain of federated learning is going to be able to do some local training on this sort of slice of the data set, learn something about that local data set, and then the notion is that you're going to share what is learned across these different institutions or different devices and so on. You're going to share it centrally and aggregate it in some way to arrive at a final model that can then be used. And so those are the core principles here, of which many people have instantiated lots of different variations of how you can do this type of federated learning. But again, the core idea is that data remains where it's collected or where it happens to reside naturally. So it could be in the hands of a user if you're thinking about a series of phones that users have and the collecting data of images, of audio clips and so on. And then through the combination of local training and then aggregation of those isolated local training elements, we can reach a model. And so you'll note here that the amount of work that is done in the data center is far diminished. And then again, if you bring it full circle and compare it to a data center style, of course, the big difference here that I've been pointing out is that the data has to reside in the data center. That's where the training occurs, and that's where, by virtue of this design, all those negative associations that occur happen. One final point I'll make in this sort of like 2-minute primer about what federated learning is that many of the arguments I'm making today are made about models that are doing classification tasks often, but you can extend the arguments to an area that's called federated analytics. And so simply put, that is just the fact that there are alternative ways of processing the data that have many of the properties that I'm talking about. But instead of creating a model that does some sort of inference, we are doing some sort of analysis on the data to maybe do some averaging, to analyze collectively what the data is showing us. And so then a lot of the arguments that are being made about being able to train a model can be made about doing, instead of doing centrally some analytics, you can do it in a distributed manner with many of the properties that I've talked about. But that's really just an aside. In terms of examples of federated learning that we can see in the wild, it's at an interesting point in its evolution because simultaneously there exists federated systems of of which that are being deployed to millions upon millions of people. So the canonical example people rely on is what's being shown here in the middle, this Google Android keyboard. And so the application being driven by a form of federated learning is in areas such as next word prediction. So every time you type a word and you're about to type the next word, there's a prediction about what that word's going to be. And so instead of you having to completely type the word out, you can just pick the selection as it sort of comes up. Now, what drives that model is trained in a federated way. And for one of the reasons being that people like to know that because it's trained in a federated way, their data about what they've been typing on their mobile phone doesn't have to be shared directly with Google or any institution behind that keyboard model. And so there are many examples of this. There is sort of limited examples in the world of ASR for hotkey word recognition being used by folks like Amazon. There are some sort of more researchy examples of people using robotics with the perception models being trained in a federated setting. It's not always about devices. As I alluded to before, institutions can participate within federated systems. So there in the UK, there's quite a bit of a trial going on right now between health institutions. And so you could imagine that there's a lot of restrictions on the sharing of data, of patient data, and yet we want to arrive at models that are that benefit from all the data that happens to be available. And so one way forward is to share this data in a federated manner. And so you do some local training in the institution, but the end result is that you have a trained model that can do things such as recognizing cancer from some type of medical imaging or any types of modality collected about patients. You have some automated way of processing data that is using fully the data from across a whole host of medical institutions. And then so you could replace medical institution here with a banking environment, a legal environment, and so on. And there's a natural reason why you wouldn't want to share data centrally, but you still want to have the best possible models available. But what's interesting here is that most of the systems that are in production, that are in use, that use federated learning techniques today can be characterized as being exciting but niche. They're toy. They are driving keyboards. They're being used to recommend, because the ones I mentioned before about some of the robotics and the hospital ones are not yet in production. And so the ones that are again, keyboard, recommendation of settings of a phone. They're of the kind where they're not very critical because it's an emerging technology. But importantly, they're not the kind of the heart of machine learning tasks that are really being used today. So then they're not touching these Netflix models that drive recommendation. They're not being used in the types of recognition and recommendation used when you do your Google searches and so on. So they're exciting, but they're a niche. And so why is that? That is because there is a long list of hurdles that are currently dampening the ability to pervasively use these types of methods. And so while we started to look at these issues, I can start to highlight some of the ones we've looked at so far. So one of these is that this reliance on labels and supervision. And so this keyboard example I mentioned earlier has this really nice property that by virtue of the task, because the user is typing in these different words and you're just trying to predict the next word that comes up, there's no need for the user to label the data. But in areas of, say, computer vision, there would be a need to somehow not only collect the data, but also collect labels within them. And so that's one of the key ways that the application of federated methods is currently quite limited, because you somehow have to have a system where it makes sense, where it's viable, that you can get the labels in the data. Another aspect that's often looked at in the literature is this challenge of non-IAD data. Unlike a data center where we can carefully create all the mini batches and structure them as we want with nice statistical properties, have them nicely be uniform and so forth, as I've mentioned, the data is going to arrive at these locations based on some sort of application-based reasoning, right? So users capturing images are going to be capturing images about what they encounter in their daily life, what they're interested in. Hospitals are going to be based on what type of conditions. The data they collect is going to be based on what sort of conditions they happen to treat. some sort of relationship between people who live nearby the hospital and so on. And so there's no luxury of being able to organize the data in a nice way such that you can maintain IID properties. And so when you start to train models in conventional ways, it's much more difficult to kind of overcome this, given the property has been broken. And more generally speaking, there's this huge overhead of communication between these entities. And if you think about this, it makes sense because normally we're training these models in a data center. They're connected by, say, GPUs with these super high-speed links that people spend a lot of effort to kind of optimize. And suddenly now we want to have these separate locations of data and compute that are tethered together with probably wireless or perhaps at best wired links that are, you know, orders of magnitude slower. And so it's obvious that training under these conditions is going to be far more difficult, because you're going to have using these slow links, and then also because of these issues to do with non-IID, the training efficiency, what you learn from each batch and how you cope with those issues also further dampens the rate of progress of the model. And so it takes longer, takes more epochs to train. And so for those reasons, federated methods really struggle. And so as we started to look at how can we solve these, we realized that in each of these dimensions, each of these ways that you wanted to improve federated learning, it was still far too hard. It was actually, it looked to us that it was much closer to the point of deep learning back in 2014 and earlier, when the frameworks were very immature, and the difficulty of doing even relatively simple experiments was very hard. You had to do a lot of coding yourself. You did a lot of optimization yourself for you to be able to train large models. And then today we can do the same thing by virtue of these tools without even thinking most of the time. And so there's a big gap that exists today between the tooling for doing federated methods and studying them and being able to innovate within them that I think is in a parallel situation to where we were with deep learning many, many years ago. And so to that end, a number of us got together to start to build a framework that we call Flower, where the main ambition is to simplify the research and development of federated methods so we can start to move faster in a direction that, for the reasons I mentioned at the start, we think are really important directions to kind of mature as quickly as we can. And so I'm not going to bore you with the components, but what I want you to sort of take on board is that as I'll sort of start to unpack in the next few slides, so to make progress in those types of problem spaces I was describing requires us to introduce tooling that makes experiments and so on far simpler, so they can be done properly and done easily. And I think the parallel you should keep in your mind is that the same way that TensorFlow and PyTorch made those experiments easier, we want to allow Flower to fill us a similar role. At this point, I should mention that actually Flower is a community effort. It's completely open source. And then tomorrow, in fact, it just happens to be tomorrow that we're going to hold our second Flower Summit of people using Flower, people building on Flower, people doing federated research in Cambridge, based in the computer lab or virtually if you want to join by those means, to discuss where we are with the project and what needs to change in the future. Tomorrow, we're going to be making a number of announcements that are really interesting for people in federated learning or who use Flower already. And so if you're interested at all, please come along tomorrow. You can go to this URL, flower.dev, and join up for the event. A couple of points I'll make is that there are a number of other types of federated frameworks that have similar intents to Flower. And so there's Google TensorFlow Federated, there's PySift, there's a couple of other ones coming up from Microsoft and Facebook. And so Flower seeks to fill in some important gaps that complement these existing frameworks. And I'll be telling you about some of those gaps in the next coming slides. But also we've been getting a lot of traction with people trying to use this system. And so and if you take a 7-day and monthly downloads as a metric of success, Flower is being downloaded at a rate that actually exceeds that of TensorFlow Federated currently. If you think that's a really strong testament to the community that's grown behind it. and the features that it enables people to do. But I think there are some strengths in other frameworks. So PySIF, for example, is very strong, turnkey, differential privacy, and so on. TensorFlow Federated interacts with TensorFlow very well. And so there are good other reasons that these frameworks existing have complementary types of skills and techniques. And but I think Flower occupies a really important part of the design space as well. And these are the core contributors to Flower at the moment. So they're either PhD students or postdocs of mine, or more broadly, these are folks in industry such as Nokia, Samsung, and startups like EdUp that are behind Flower, trying to build it and make it a useful environment to do research. So that's enough about Flower and what it is. Let's get back to some of the motivations and why it's useful as a researcher. One of the key elements is that when it comes time to evaluate your federated system, you want to see how well the accuracy of the model is going to be, given your new and exciting type of federated aggregation scheme. What we noticed was that most of the papers in the literature, when we started and even today, evaluate their methods along the lines of something you see here in terms of code. And what they are, they're evaluating this ideal of a distributed system that's very scalable. You either have a dozen types of institutions with lots and lots of data, or you maybe have millions of different devices with small amounts of data collaborating together. And they evaluate their method on a single machine where each of these clients might be a single element within a for loop. And so obviously this is going to neglect a lot of different important issues to understanding how successful the innovation that you're trying to analyze is going to behave. And obviously there are things like networking to account for. There's the variations in compute availability, sort of very practical issues. But even if you put those practical sort of device-centric issues or institution-centric issues to one side, there's this key issue of scale. It's impossible to scale that type of system that you see in a way that are sort of described on the left-hand side that's representative of how folks are evaluating them. So the issue of scale is critical. And so as an example, when you look in the literature of people looking at distributed machine learning methods, we picked, I think, 100 recent papers that were, I guess, selected by the number of their citations. And then what we found is that this is a histogram of those papers. And so on the x-axis, you see the number of clients that they're using to evaluate their methods. And so what you see is that most of them are evaluating with 100 clients or less, even though that most of the motivations, most of the reasons why they're interested in building out these systems are of this device-centric view, where you might have lots of smartphones collecting, say, audio samples, trying to train a distributed speech recognition system, as an example. And so the problem here is if you only evaluate under 100, you're going to miss important parts of the design space. You're not really going to understand if you've done a good job or not. And so just to preview, one important exciting aspect of Flower is that it enables people with, say, 4 or so desktop GPUs, maybe in some sort of academic cluster, to simulate federated systems and then evaluate their new exciting technique at a scale that's impossible with any other framework. And so these blue dots you see are the papers that were in the prior histogram. This red dot that you see across, it's just, it's in the bottom middle. That's of the closest competitor that's looking at how do you simulate and scale a system called FedScale. And in the top right, the top right, you see this green star, and that's where Flower occupies in terms of just being able to instantiate a simulation and evaluate it to see, is the method going to work well or not? And so it's been able to, with resources that are available to academics or small scale labs, allow folks to start to understand federated learning at a scale that's important and that they're otherwise able to reach. And so what I also want to draw attention to is if you go back to the papers we saw before, you'll see there are some papers looking at large scales. So you can see these like these bins of one paper judging their methods at above 50,000 clients and so forth. And that is a design space that's only being occupied today by large corporations. So by Google, by Facebook, by Tencent. And so what we want to be able to do is allow, one of the important dimensions of Flower is to allow folks to start to evaluate their methods at that scale, and using a tool that is completely open source and community driven rather than something that's being guided by a corporation. So one question would be, how do we do this? And so let me just highlight, there's a couple of key components in the framework that I won't mention that allow us to do this. And I want to just fast forward to the method itself. But before I get there, I will highlight how easy it is to use Flower. So you can have a machine learning pipeline. So you might have, so basically some code you've written in TensorFlow or PyTorch. Perhaps you've trained it and you've built it, designed it in a way that's going to operate under a centralized fashion. And then you can start to look at how that particular task, I guess it would be, how that task is going to operate under a federated setting with only about 1 or 2 lines of code. And so it's written in Python, and you can wrap these existing methods for doing different tasks really quickly and evaluate them using existing methods that are implemented in Flower that are well known, things like Fed average and so forth, or you can sort of roll your own and test how it's going to work really quickly. Before I show you, just discuss how, let me also show you a couple of results about scalability, not only in terms of the amount of clients that it can support, but also in terms of speed of being able to train, because it's also another dimension of scale. If you look on the left-hand side, I want to show you training evolving over a series of rounds on a non-trivial architecture that have Dilbert, so a compact transformer that's being used on an NLP task. This is one of the largest NLP data sets that we could get our hands on in terms of recommendations. It's offered by Amazon. And you can see that we've just configured Flower to start to train this in a distributed manner over different configurations, ranging from the total number of clients in the pool is 15 million. So that's unheard of. And then per round, you do sampling of clients from this total population. So then you can see that we can crank this all the way up to 1,000 clients. And of course, the accuracy increases as we start to involve more clients per round. And you can see that training is actually able to successfully complete. If I look at scalability also in the direction of how fast is it occurring, it's not only can it occur or not, like a binary, but how fast is it? And we compare it to other frameworks, you can see that in many cases, Flower is much faster than the existing frameworks. And so one of the fastest simulation frameworks that has been developed so far is something called FedJax. FedJax is in the light blue. And what's important about FedJax is that it achieves its scale by not using any conventional training framework. So you cannot use a TensorFlow framework, you can't use PyTorch. And so you'd have to write every time you want to evaluate a task, if you want to have a new exciting algorithm for doing aggregation or some type of federated method, and you want to see how well it'll work on a particular task, some computer vision task or whatever, you'll have to rewrite that from scratch in JAX for you to be able to see if it's going to work. And if you're willing to do that, if you have the time, then you can get, in some cases, faster results. This is log scale, Flowers in green, FedJax in blue, and the setting is very simple, 3 clients, and then you're just doing 1 epoch per client. So it's a very low weight configuration. But if we just start to make this configuration more complex, maybe increase the amount of local training to 100 epochs, you can see that FedJax, even with the limitations I mentioned, also starts to slow down dramatically, whereas Flower's rate of speed increases is less. If I compare Flower also to something like TensorFlow Federated, there in the purple, you can see under this configuration, TensorFlow Federated is quite a bit slower. And then you can also see in the orange, although it's not highlighted by an arrow, Fed scale being much higher than any of these other ones. And so the point here is this, that our method can scale. You can have arbitrarily large scales that are much larger than other ones. And also the time it takes to train using existing infrastructure that is common to an academic or to a small organization, these can be done at reasonable speeds, and particularly in comparison to other methods. So how is this happening? Well, it's being delivered with an approach to distributed training that has some groundings in conventional data center scale distributed training. What we want to do is have a simulation of a lot of different clients and then instantiate the resources that we have. So you might have, amount of memory related to the each GPU card you happen to have in your desk or data center. You might have, say, 4 1080s, we'll say 12 gigabytes each. And then the main allocation problem that Flower wants to solve when it has the scalability is to instantiate the clients appropriately to those that are being active. So in the case of, if you have a huge population of federated clients, they're not all active at the same time. So it cleverly wants to use the memory of the GPU only on those clients that are going to be active now or in the near term, so to preload. And then it's going to want to use the cores of the GPUs to do the work of each of these live clients scheduled in a way that you're maximizing the throughput. And so it's very similar to how HPC cluster is going to allocate jobs to a distributed GPU to maximize throughput. Except here, we're doing so to simulate a federated training loop that is doing local training in isolation and then doing aggregation in terms of simulating the server, which is very different to how conventional HPC training is going to occur. We don't have some of those properties. But by solving this problem, and the details are in the paper, I just want to give you a sketch of the solution. By solving this problem, we're able to have these sort of really exciting throughput numbers that you saw before. Also of extreme importance is the ability to interleave real devices. So if you really want to be able to understand if the system is going to work, it's very valuable to be able to have, for example, one phone, one IoT device within the loop. And so you can transparently add real devices to your heart's content to have a increasingly realistic simulation of the federated system. And so this is an important dimension that's been absent from a lot of federated frameworks up until this point, that are now available within this framework called Flower. So just to kind of summarize some of the real aspects, some of which I've mentioned, I've talked a lot about scale, but others I've sort of not talked about. What Flower is trying to deliver to the researcher is the ability to do scalable experiments, also to do sensitivity analysis on important factors that affect the sort of convergence or behavior of their algorithms, things like speed of network, wireless, the amount of compute per node. It turns out from our experiments that existing algorithms like FedAverage behave very poorly when you have heterogeneity and the compute available to different nodes. You can actually study these effects from Flower really easily. And most importantly, it enables you to do systematic, repeatable experiments, like apples with apples comparisons with other people's approaches and your own, using a common set of tasks. And so we think that's sort of hugely valuable for people who are wanting to push distributed learning forward. So what I want to do in the last part of this talk, now I've talked a lot about Flower, is just walk you through very briefly 3 different case studies that either we, or in one case, an external set of researchers have been engaged in, in each case have pushed federated learning forward in some particular way, all using Flower. So the first of these is work done in my group that was I think it's the first time that people were able to train a federated model for full speech recognition tasks under a setting that is much closer to what you would expect to see in a federated system. And so this is work that was presented just last week at ICASP. Again, so the setup is we want to study real world ASR. We want to be able to train a full end-to-end ASR system using the latest architectures and losses and so on that people in that space use, but we want to do it in a federated way. And so we use Flower to set up a very realistic setting, and we found that the existing methods that had been published a couple of times on smaller scale data sets, on different sort of problem settings to do with speech recognition. So for example, the learning of a small snippet of a hotkey word recognition, say, hey Alexa or hey Google, those type of things, which it's not full-blown ASR, but it is definitely obviously a close cousin to ASR. We found that those methods failed. And so what we found by setting up a realistic setting was a recipe that I won't go into that enables you to train a full-blown ASR system under much more realistic settings that are closer to what you'd have in a real federated system. There's a couple of key things that we found to be necessary. One was that the aggregation phase of in the federated system had to change. Instead of it needed to change to be based on a specific word error rate weighting strategy. Second, we found that it was necessary to have a very small cold start centralized model trained. And so we tried to find ways to minimize this as much as we could. And you'll see in the results page that the cold start, meaning that you have to have a small model trained with a small amount of users centrally before the whole thing would converge, could actually be quite small. And so this is the setup. Most of the time work of this kind had been done using Library speech. The problem with doing Library speech is that it doesn't approximate at all what the federated system would actually encounter, because these are just people reading with a very clean acoustic background, and where the variation between speakers is minimal. What we used was a dataset called Mozilla's Common Voice. We used the French version, and this is great because it's captured from laptops. And so you had a very dynamic acoustic environment of different people contributing data. Also, the diversity between speakers was very high. And so this is much closer to what you would find in a real federated system if you want to train that from scratch in the wild. With some approaches, we were able to reduce this warm-up model to only requiring 117 speakers. And from that core sort of model, you could then train the rest of the system with distributed data coming in from 4,000 different speakers. And we did a test set with, again, another 4,000 speakers. So in total, we had a lot of different users, much larger than you have, for example, in Library speech. And then, although this acoustic setting is very hard, so the word error rates are larger, what we found to be very promising, if I just move to the slide, was that the word error rates between the federated conditions and the purely centralized were very close. And so we think this is an example of being able to do federated in a very challenging environment where the level of realism has been kicked up a long way. And through the sort of experimental approach you can take with Flower, because it's quite realistic, we're able to find a solution that we didn't find in literature previously. The next case study I'll just sort of briefly describe to you is in the direction of carbon footprinting. The key issue here is, as I mentioned much earlier in the talk, was that in centralized forms, there's an alarming amount of carbon produced. We thought it would be really interesting to be able to profile what are the different types of carbon footprints for different settings of federated learning. And one reason for that is that the type of analysis that you see here on centralized settings only really came out after people had kind of locked in the way that we're going to do centralized. If we had some of these results earlier to do with the carbon footprint of existing centralized settings, perhaps we would do things differently. So if we could fast forward and have an understanding of how federated and carbon interact, perhaps we can influence the way that it evolves in the future. That was our motivation. And so we developed a carbon footprinting method that could look at both federated and data center settings and compare the two. I won't go into the details of the model, but it essentially needed to extend upon the core of Flower that can provide very accurate estimates of how long it would take to train. So wall clock time, it can provide for individual devices, estimates of what's the energy are going to be required for those devices, how long are they going to train, or all sorts of just system measurements can be provided at an accurate level from the framework itself. And then what you need to do and build on top of that is a framework that enables you to estimate the carbon footprint that extends from how much electricity it uses, how long the train takes, and so on. And so a couple of key aspects would be, in the case of federated, that distinguishes the carbon model is, in the case of federated, there's no cooling required, but it's much more complex to understand the carbon effects of the data transfer and storage, because depending on different settings, it's going to use wide area links, some of them wireless, some of them not. And so you need some way of modeling that. You also need to be able to model what happens when you have devices in different countries, because each country is going to have a different conversion rate between how dirty is the power they use. So obviously France heavily with nuclear is much more carbon friendly, even though you might be in comparison to something like China. And so we needed a way to capture that. And so we have a couple of papers now that look into this issue. I just want to pull out one result so that you could kind of see what is possible from this model. And one of the things, it's an interesting result. We found that in some settings, federated could even be more carbon friendly than centralized, which was a bit surprising to us because it takes a lot longer to train, a lot longer to train. The devices are a lot weaker. They have to pay this penalty of having to shuttle data over long distances. And so we were kind of surprised to see that even in current settings, there could be situations where federated was more carbon efficient than centralized. And so one of the outcomes of this method is that we now have a way for the first time to be able to understand when is something appropriate for federated and when is it appropriate for centralized in terms of the carbon footprint. This happens to be for training a computer vision task that of Safari 10. We want to train it to 60% accuracy and compare a reasonable data center against a federated system. The federated system is fairly advanced. It's assuming Xavier and X edge devices that are probably one of the fastest embedded GPUs you can get today, but it won't take many years before they're just standard in everything. Right now, you'll find them in high-end IoT cameras, tablets, maybe some robots, but a few years' time, these things will be in all the different edge devices that you see, something equivalent to it. And so we think it's a reasonable comparison from that point of view. So in this particular setting, you can see that federated is 1.7 times more carbon friendly than its data center cousin. On the right-hand side, let me show you one figure that helps you understand why that's the case. And so what we found is that federated systems per epoch are far more carbon friendly, right? So for each epoch, because there's no need for them to cool, each individual device is drawing a lot less power. So in terms of each epoch, they produce far less carbon than the data center, if you compare those blue and red lines. And so because of this fact, because that gradient is so shallow, then even though they're far slower to converge to the same level of accuracy, there can be settings where they're able to still be more carbon friendly. Even in this case, this is a different case, this figure, but in this particular case, it's taken 8 epochs for the federated system to reach the same level of accuracy as the data center, which only took 2. But the gradient is so much shallow on the federated slide, its carbon footprint is still less. And so that's one of the factors that we saw coming in to these results. I'll just close with one last case study, just going to blaze through it. It's from a different group. I happened to also head the Samsung AI lab in Cambridge. They used Flower to study a very novel problem that was very Samsung specific. This was in the direction of device heterogeneity. And so let me just acknowledge these authors coming from a different pool that I've been referring to so far, and explain the problem statement. And that was, most of us who've found federated systems or looked at these federated settings before know of this issue to do with data heterogeneity and the difficulties in modeling that they present. But a similar parallel set of heterogeneity exists in the system dimension. And essentially because different devices of different capability can vary widely. And yet we want to be able to learn from all the devices, because valuable data might be existing on an edge, on a very weak edge device like a watch. There's often going to be a lot of correlation between perhaps certain demographics having cheaper, less powerful devices, or certain locations in the world where data is collected using devices that are comparatively a lot weaker than those from other countries. And so we need to build federated methods that are going to work irrespective of the varying system dynamics, the amount of memory, the amount of compute and so on that exists between them. And as far as we could see, there was very little work, if not no work, that provided a federated solution to this problem of having large heterogeneity between your systems participating in the federated setting, and having them able to participate fairly. And so the system they came up with is called Fjord. It's a design of a neural network that you can basically scale the width and in the style of training, so that you can basically narrow the network for simpler devices, complete the network and expand it all the way up for the most high-end ones, and train in a way that the weights that are learnt even from the high-end devices can benefit the low-end and vice versa. So it's that in one method is what the idea seeks to try to do. And then when we did the evaluation, there was, against a lot of tough baselines trying to do the similar things that we could think of, the Fjord approach was the far best in terms of the amount of the accuracy it could achieve, and the convergence that it could achieve those under. And so I just quickly want to go through this final case study before I start to have discussion with you all. One particular thing I want to give you was some food for thought that might provoke some discussion. And that would be that I would like to highlight that I think as federated learning starts to mature, and if it can start to combine with similar maturing of self-learning and unsupervised methods, I think the combination of these two things is going to unlock a lot of use cases in the federated space that we see right now closed. And so my prediction would be 3 years from now, we're going to have example systems used commercially that are going to be combining ideas of federated systems and things like self-learning or close cousins, that where we see the federated system actually outperforming the data center one, because most of the data, if not all the data that's useful, will actually be captured on the edge. It'll be available without any domain gap. It'll be able to be computed upon locally and not having to be shifted all the way to the cloud. I think we're going to get to a point very quickly where there'll be so much data collected at the edge that it'll be impossible for it to even be shifted all the way to the data center. So the data center will actually be having less data available to it than the federated one. And once that happens, we're going to see these federated systems actually outperforming the data center ones in particular classes of application. So those that are very consumer facing, those where local data really matters, those where capturing data in a curated way that are representative of the task is very difficult. We're going to see some big changes. If we start to see these systems where federated are beating data centers, then there's going to be a huge paradigm shift for a lot of the industry, not all of it, but a lot of it. And I think it's coming much faster than we expect. And so with that, I'm happy to take questions from you all. And if anyone is available tomorrow and wants to come to the Flower Summit, you're more than welcome.
Thanks, Nicholas. We have time for questions. I hope you can just open your mic if you have a question. Maybe I can start with one of my questions. So,
sure.
I sort of feel that it's an uphill job at the moment, that the comparison between federated learning and sort of centralized learning is a little bit unfair in the sense that they're not achieving the same thing, but that seems to be sort of the currency of you're sort of trying to say, well, can we do federated learning well enough that we can sort of compare to the centralized system? Whereas some of the things that you talked about right at the end was about, that's not really the fair comparison. The fair comparison is, systems where the data simply does live on the edge, et cetera, et cetera. So there isn't a centralized thing to compare to. So do you think that really, to me, that seems that really needs to change before federated learning becomes a real alternative? Is that unfair?
Well, I think there are a couple of separate motivations that are happening at once. And so one of those will be the one I mentioned at the end. So where if we can start getting really good at unsupervised-ish methods, then suddenly there's an avalanche of data we want to get access to, and then it'll just be unaffordable, I think, to ship it all to the data center. And so then there won't be any option. That's one motivation. Another motivation for Federate, I think, is going to come from the point of view of being able to access data sets that are, that are too cumbersome to combine. And so then there's a lot of interesting data just sitting in organizations where it's just too much effort to, there's legal, but also just a kind of like organizational effort to bring them together. And so I think even though there might be good reason if you could put them all in one place to learn centrally, and that model would perhaps be better and easier to do. But I think if Federated can give those folks, those settings an option, where you just sort of turnkey, you're ready to run, then again, that's another place that'll kind of start to gain a lot of traction. So I guess there's a lot, I would probably, some of the, so I guess you might have noticed that some of my logic underpinning why I think it's so important is almost a little schizophrenic in that it's kind of coming from two or three different places at once. And that's because I'm trying to kind of combine a few different sort of motivations that I think speak to the kind of invention and maturing of these methods that perhaps I think often are motivated most often by user privacy ones, which I think is just a thin, actually sometimes in some ways it's a thin argument too, because it depends on who you trust. And like, do you trust the code running on your device? Maybe you don't. If you don't, well, then maybe you shouldn't worry so much about is your data being shipped or not. But yeah.
Anyone else has a question? Okay, seems to be not be the case.
Sure.
I guess.
Yeah, well, I mean, I suppose one of the things we could talk about is that I think that there are some interesting machine learning problems to be tackled that right now are just, the way I feel about it is that they're just too hard for students or researchers to really tackle. And so then I think they're kind of gravitating towards things that are easy to access and ignoring some problems that are rich and waiting to be examined, but they can't either do it because it's too hard, or maybe they can only do it in such a superficial way. Maybe it's hard to get those things published. And so that's one of the kind of things we've decided to invest a lot of time in trying to narrow that gap, versus maybe trying to find some secret source, because we think the secret source will come next. Or we're doing our job if we can help people find that secret source anyway, build the community.
I certainly think that's a great point, that a lot of our community is very much geared toward what can be published, right? And even if you're solving an important question for an end user, it might not have the academic appeal, sure. and that can be a huge influence.
Sure. And even also it helps people focus on perhaps what they're best at. So if you can widen the tent and let more theoretical people jump into an area, if you can make it kind of as accessible as some of these sort of deep learning frameworks have made it. So I think that's something that we're trying to help with.
All right. Well, thanks a lot, Nicholas. It was a really stimulating talk, and something sure. a little bit different than from. So thanks very much. And,
sure. Thank you for the invitation.
Thanks for everyone for coming.
Okay. Take care.
Bye, everyone.
Bye-bye.